Hi YouTube, mailbag video today. We're going to look at the DPH5005 power supply. It's a buck boost power supply, max power 250 watts, input voltage range 6 to 50 volts, output anywhere from 0 to 50 at up to 5 amps. It's adjustable, and I had ordered the set including the steel case and Bluetooth/USB output modules. Which allow for some control via phone app, etc. Ordered it for about $50 US, though I think it's gotten more expensive and it's closer to 60 or $70 US now. And I've heard good things about it. Not the greatest ripple current, but good enough for my purposes, and it's a kind of go anywhere, do anything module for me. Alright, so when I ordered it, it came literally as is in this packing tape and styrofoam ice cooler configuration, but the inside seemed reasonably well packed. This is the steel case. We have the actual power supply module itself, and what they call a gift, which is the crappiest alligator clips possible. Alright, so on the packaging itself, they actually list several different models of power supplies that fit inside this case, and list kind of the hardware contents by picture. Seems reasonable enough. Comes in bubble wrap. Not the most secure packaging, but I figure it works for the cost. Get rid of that real quick. Stamped and folded steel case. Oh, a couple screws holding it together in transit. That's a bit of a good sign, considering that without those extra screws holding it together, it probably flies all over the place and the metal scratches itself, so I can appreciate that. And in fact, while I'm at it, let me just drop things all over the place. Make sure that that doesn't go anywhere. Alright, steel case, open up. Lid, nondescript. Extra contents. How much tape did they use? Did they tape all the way? Alright. What do we have here? We have the Bluetooth. No, this is a input board. This appears to either be an input or an output board. This looks like an input board. I'll insert a close-up here in a moment when I go through each individual component. Additional hardware pack, including some spade connectors, extra screws, standoffs, washers, miscellany. We have more hardware, a rocker power switch, decent positive click to it, doesn't feel too cheap. As I continue to drop things all over the place. We have some binding posts. I'm usually a critic of binding posts, and I get pissed off at cheap ones. Let's see, how do we know if it's a cheap one? First off, does the binding post nut completely unscrew? No, that means it's captive. Good. The next question is the insulator keyed? You'll notice that on the case itself, I'll put my hand behind there, you'll see it's got the double D pattern, where there's two curves and two flats, to make sure that the assembly doesn't twist. So presumably the insulator is also keyed correctly, and it is. The backing nut is not, but that's fine. And I guess the last check is, what's the base material? Is it tin-plated copper, or is it something like aluminum or steel? The really good ones are copper plated with something like silver or tin. The cheap ones are steel and magnetic. Okay, not magnetic. The nut or washer is, but that's fine. The actual binding post metal is not. So let's just do a quick check with a file. Well, it appears to be contiguous in color despite filing into it, so that means it is aluminum, which means you can strip the threads out a little more easily on these binding posts. Not the greatest, but you know, for what this kit provides, probably the best that can be done. So, binding posts. And we have a little bit of black and red wire that appear to be slightly different length, and they are PVC jacketed, not silicone jacketed. Is there a temperature rating on these? There is no temperature rating, though there is an IEC 60227 IEC02 RV, and is rated to 450/750 volts. So that's probably 450 volts DC, 750 volts AC. I would have liked to see silicone wire inside, but it's internal and not subjected to too much friction or vibration. So we're probably fine. And we have a DC fan. I don't know whether this is a ball bearing or a bushing type fan. 5 volts DC. So that looks straightforward enough. Alright, so for the actual DPH5005, we have a foam insert packaging, non-ESD. They actually have a download link for the app, I guess, and a registration card. Let's see, we have the Bluetooth board, as well as the USB, not USB host, USB client board. So I'm guessing it just sends serial data. And unfortunately, I've done a little bit of reading about this. You can only pick one of the two and plug it in with that little header cable to this port here. However, you have the option of installing a little toggle switch and switching between the two outputs, so I'm probably going to end up doing that. We've got two JST style cables and the keyboard display module with a rotary encoder, click button, couple clicky buttons, and on the back side that looks like it just comes off LCD and keyboard connections to LCD and keyboard. So that's straightforward enough. Alright, I've tried to set this up as nicely as possible to give you a really clean overhead shot, and I've got my plastic spudger to help point out components. We have power input, which appears to be 4 terminals and is actually a detachable connector, which is a nice bonus. Makes it easier to service and wire. So 4 terminal input, 4 terminal output. We've got a current shunt on this side, as well as, I believe, one other current shunt? No, it must just be the one current shunt. We have a heatsink with a fan and 2 transistors or MOSFETs, buck side inductor and a boost side inductor. What looks to be this little board here featuring a Linear Technologies LT-TSX chip, so I'm going to have to look up what that is. Okay, so after doing a bit of reading, this daughter board features an LT-1871 boost controller chip surrounded by a couple passive components and a couple inductors in the neighborhood. We've also got these 2 SOIC 8 chips with kind of a mystery part numbers on both of them. I tried looking them up and they yield no results. Chances are we have the input power here, and one of these diodes, capacitors, inductors, along with one of these 2 SOIC 8 chips form the bootstrap buck circuit, and then this circuit here forms the bootstrap boost circuit, and probably provides a regulated output for the microcontroller and some of the glue logic over here and possibly here. What is that chip? Oh. Either way, we have a series of capacitors for the buck and the boost, 2 transistors, heatsink with a fan. So that's the buck, that's the boost, and we have the output. Pretty straightforward. We've got the ground, transmit, and receive for serial connector on this 4-pin header. Probably the 4th pin then is 5 volt for either the Bluetooth or the other USB transceiver logic. And on the underside of this board, it's pretty nondescript, just an insulating washer on the heatsink, which is interesting because the 2 transistors are already isolated from the heatsink, so I'm not quite sure why they decided they needed double isolation, because that's extra component count and extra cost, but clearly they felt it was needed, so good on them for doing that, I guess. And if we look at the buck boost module, we see a 32100F microcontroller. That's an ST Micro 32-bit microcontroller that's 3.3 volt logic, and has a bunch of features which seem like a little bit of overkill, but it is driving the OLED display in a quasi-real-time manner, so maybe it's not overkill, plus it's not a terribly expensive part. This microcontroller chip, this 32F100, I thought it was overkill, but looking up the price, this is almost a $10 Canadian component. This isn't a cheap component, so it must mean that the computing necessary to run this and the front panel display is, I guess, warranting such a microcontroller. And on the module itself, an interesting feature, I'll have to refocus here, underneath the fan, you'll notice that there are 2 more MOSFETs hidden underneath, and this washer is probably to some degree a means of controlling force against the 2 MOSFETs. So there's the 2 components here, the TO220s, and these what is it, DPH5005 style MOSFETs, along with a couple more passives, including even like a little MELF resistor package, and some more ceramic chip capacitors and resistors, including that big guy there. It's an interesting configuration, to say the least. It is space economized for sure. Hopefully this never blows and needs servicing. Other than that, we have some click-in style standoffs, and that's the actual buck boost board itself. The keyboard display module, pretty nondescript, clicky buttons, rotary encoder wheel with a click button function, and on the inside, nothing particularly spectacular. You can see the solder points for the rotary encoder, and an 8-pin header connection for presumably the OLED display. And you can see on the background there's a couple vias, so the clicky buttons are probably surface mount on the opposite side, and that's why we don't see any through hole here, because there's just simply not enough space in this assembly. If that's where the PCB is and that's where the buttons are, there's really no more space for a separate second board for additional through-hole components. And in fact, it looks like I could just spudger my way into here. So in theory, if I can just pull this knob off, maybe I can... Hey, there we go. Yeah, so as we suspected, we have SMT buttons. We have a 8-pin header interface for the OLED display, and one more button and a rotary encoder. Pretty nondescript. Some standoffs here which act to prevent it from being forced all the way in and hold it at the correct distance. So I'm going to put this back together real quick. Quickly before I reassemble this, just taking a look at this front bezel. This is actually a 2-layer component. So again, more assembly steps, more value for the cost of this buck boost power supply. You've got the acrylic or polycarbonate layer underneath that provides rigidity, and then you have this top layer which is just an adhesive polycarbonate layer with the membrane buttons. Nice touch. It provides the cosmetic cover-up for the PCB underneath while also providing some rigidity. This front bezel seems to transfer all the force through the PCB and these 4 headers. The OLED display frame and the 4 headers. So even if you poke here on the perimeter, it's pretty solid, and you'd have to push pretty hard in the center to get the OLED display to take any pressure. So reassemble all this should be pretty straightforward. Just shove it all in. Here's the input power board or module. It looks like you have the input terminals here. You've got 2 output connections which says key, which doesn't make any sense because the keyboard module only has JST style headers. Presumably these 2 solder points go to the actual buck boost module itself, and the rest of this appears to be a buck converter of some sort that takes it down to 5 volts for this 2-pin header connector on the fan. And the output circuitry itself appears to feature a small tantalum cap. I don't know if I can see the rating on that. It doesn't say what the rating is on that cap. I'd have to put an LCR meter on there. But this board seems relatively straightforward, though there's this fairly sizable transistor on the back, so that's kind of interesting. This transistor is a through-hole component, but it's mounted as if it's a surface mount component. You'll see here these 3 pads, and there's actually this SOIC 8 footprint here with all 4 pads paralleled on both sides. This is isolated and these 2 pads are connected. So my suspicion is that this is actually an input protection diode, and they had the option on this board to put a SOIC 8 footprint or a TO220 output footprint. Actually, no, sorry, I'm mistaken. This is not a input protection diode because this is not paralleled. There is a very thin trace hiding in behind here that goes to here. That pad is common to this pin. Either way, it's interesting that they take this TO220 and mount it as if it's a surface mount component. And I just noticed it's marked Q4, so it's definitely not a diode. So that's interesting. This must be a power switch of some sort. Oh, you know what? Maybe it's a soft power switch where the rocker switch connects to these 2 terminals. I'll have to read the instructions on assembly here. Fairly nondescript looking. We've got a Bluetooth serial module, castellated pins on the outside used to mount it to the carrier board, 1 bypass capacitor, and what looks like ground, receive, transmit, and plus V. We've got another what looks to be an LED and a resistor. So there's minimal circuitry surrounding this. There's 1 little ceramic resonator in there with 1 component that handles all of the Bluetooth magic. The rear reverse side just has the data lines broken out and fed to whichever of the associated relevant pins are on this side. Not much to remark here on the Bluetooth board. So the USB transceiver actually ships with the USB cable pre-populated, so we're going to have to just disconnect that for the moment. What do we have here? We have upside down. Alright, so the USB transceiver has a CH3400, sorry no, a CH340G chip. It's kind of like an FTDI USB driver chip, except it's the, I guess, Chinese equivalent of it. Lower cost without the licensing, but it does the job for low rate serial. You've actually got a crystal in here instead of a resonator, and you've got a couple of pretty sizable transistors, U5 and U6. So that's kind of curious. Maybe this is input level shifting. You've got more transistors. There's remarkably more on this board than should be on this board. If this is just a USB to serial board, seeing such large transistors, these two components, and two more, makes me think that there's some sort of level shifting going on here, and that the actual controller itself is 3.3 volts. So a brief addendum to my comments about the USB transceiver. I was mistaken. I took a closer look, and these two appear to be optoisolators. So the serial, transmit, and receive power and ground pins are all optoisolated from the actual USB side, which is great because it prevents ground loops. For the most part, it also looks like the ground fill underneath is not common with the ground from the data lines. So this is actually pretty well thought out. Here's a sped up time lapse. I'll just speak about some of the highlights during assembly. I can definitely appreciate how they included nylon standoffs for the opto-isolated USB port. The binding posts were okay to install, though one of them did have a bit of binding and seizing. You'll notice that I'm labeling cables. That just makes it easier to tell one from the other. And another small detail I can appreciate is how the fan actually has a hexagonal indent for an M3 nut to sit. They're not perfect friction fit, but I can definitely appreciate those small details. Wiring was a bit of a pain just because they didn't have any guide as to how, and they actually seemed to shortchange on the black colored wire. Once the input board was finger tight on the binding posts, I actually found myself needing a socket wrench to get into that tight space. With the input board installed, the next step was to install the buck boost module itself, wire up the display, the USB port, and the power wiring. I'll have to go back and install that Bluetooth module with a switch later. After that, wire up the rear switch and just do some initial testing. Alright, so I've got a little test setup going. You can see in the background I've got my power supply set to 7.5 volts. Idle, it draws 0.23 amps, which works out to whatever wattage is on screen here. You can see the input voltage down here at the bottom, and to adjust settings you can just press the V button, change your digit position with the encoder, and say I want to dial up 20 volts. Then you just commit it with the button according to the parameter you're trying to change. So now I want to change this down to, say, 100 milliamps. No, stay at 100. Alright, so 20 amps, 0.1 milliamps, sorry, 100 milliamps, and power button. 20 volts. Close enough. And it's drawing a little bit more power in the background, but nothing spectacular. Now let's turn this off and see if constant current truly works. I'm going to swap my probes and move this to the 10 amp position and switch it to DC amps. Let's see if this works or smokes out, because the fuse in here is something like, I don't know, 60 bucks. It's in constant current mode. You can see the CC. We're about 100 milliamps. If I turn that off, it'll go back to constant voltage. So let's adjust the current setting. Let's go up by 5 milliamps. Yeah, I seem to have some pretty fine control here. It's not exactly bang on with the fluke, and I'm not sure which one to believe. Actually, no, it is bang on with the fluke. 124 milliamps, 124 milliamps. The set point and the process value are still differing. Maybe there's a small offset by about a couple milliamps. It's something I can tolerate. I mean, if I crank this up to 200 milliamps, what do I end up with? Four milliamps offset. Okay, so it might just be a linear offset from the set point. And knowing that I'm in constant current mode, look at the voltage is 20 millivolts. So I'm going to switch back out of this mode. And actually, I'm going to just do it by disconnecting that probe. We're back up to 20 volts. Now, if this were high voltage, I would not hot plug like that. Now let's try maximum voltage. What's going on here? S over voltage protection. Oh, I think I accidentally exceeded the over voltage protection. Let's just call it 51 volts. Power on. 49.8, 50, close enough. That's certainly going to tingle if you got your fingers caught in there, so I'm going to avoid those terminals right now. But, yeah, it seems to work pretty smoothly. Other than the fact that your controls are so close to your output terminals, I'm reasonably satisfied with this. I'm going to have to go look at a little bit more of the documentation, but ultimately it seems to be doing okay. I'm going to have to do load tests and thermal characteristics, or thermal characterization, but that's for a future video. Quick and straightforward. Needs a little bit of finagling with the wiring inside, a little bit of cleanup. I will eventually come back to install this Bluetooth module, though it remains to be seen how 2.4 gigahertz is going to get through this enclosure. I will want to do a full load test with a thermocouple planted on this heatsink and run it at varying wattages to see just how the thermal performance behaves. And I will eventually want to fiddle around with the serial control. The company that manufactures this does publish the serial protocol, so it shouldn't be too hard to write a little bit of code and provide some external control. Otherwise, if you like this video, please like, subscribe, comment, hit the notification bell, and if you have any experience, good, bad, or indifferent, with a DPH5005, leave a message down in the comments below. I'm very curious to see how other people have gotten on with their power supplies after some thorough use. My ultimate end use for this is going to be for the lithium titanate battery bank, because I want the ability to take almost any voltage and boost it up to a float charge voltage of 15.7 volts. It won't matter what the current output of this is, simply because of the fact that those lithium titanate batteries can charge at like something, I don't know, absurd. 10C at 40 amp hours is like 400 amp charge current. I'm never going to charge it at 400 amps. So if I trickle charge it and steal power from literally anything, a USB, solar panel, anything, this will do the job for me just fine. Otherwise, peace out.